Hi, in this video I want to talk about star hopping, and I want to discuss this technique that is commonly used by astronomers in order to hop from a visible target directly to their intended target that may be difficult to spot. So let's consider we can see the 7 main stars of the Ursa Major everywhere, even in the city. But it will be very difficult to see the galaxy, the many galaxy that is around Ursa Major. We have somewhere here, we have the Pinwheel galaxy, somewhere there we have the Whirlpool galaxy, then here there is the Bode and Cigar galaxy, the Sunflower galaxy again there, and I'm sure there are many others. So we cannot directly see them, and those are not really close to a star that we can use as a referiment. This would be an example for, let's consider one instance that we are interested to frame, to photograph the North American Nebula. What we do is we know that is in the Cygnus constellation. We can go to Deneb, the brightest star at the tail of the Cygnus, and if we can zoom in a little bit, let's suppose that yes, we can simulate the field of view of my Olympus camera with a 300mm lens. So that will be the field of view that is equivalent to a 600mm lens on a full frame camera. If I center Deneb or I push it a bit on the side of the frame, I can pinpoint, even with this narrow field of view, I can see some nebulosity, and so it will be just one test shot, and then I can simply refine and I go there, no problem. Now, if we want to do that with galaxy or with other target, then things may be a bit more complicated. Let's consider again, let's go back to Ursa Major, and suppose I want to do the Pinwheel galaxy. This is a 200mm lens, and even if and you see that the pinwheel is somewhere there, I cannot pick it in a 200mm lens that is 400mm on a full frame. I surely cannot get it easily in the frame with a 300mm lens. I may get away with something like 135mm, maybe, yes, because I can take Mizar, that I can see Mizar, and I know that up there somewhere there is the Pinwheel galaxy, and so I can do this game here. Or I can do the same game with this rather wide view. I can do that with Alkaid, and then if I zoom in, you see that here we have the Whirlpool galaxy. Now, this would be great and pose no problem for wide field star astrophotography, but if we start to talk about close in to the target, let's suppose with a 300mm lens on 600mm lens on full frame camera, or we go, I don't know, we put a Barlow, then we can nicely fill the view with the Whirlpool galaxy, but now we have really no idea where Alkaid is. And if we start from Alkaid, or we start from Mizar with this kind of instrument, then will be very difficult to find our way in order to frame the pinwheel galaxy that is there. So in order to make the process easy, there is this star hopping technique. The idea is that we are going to frame a visible target that is relatively close to our intended target, and then we use stellar coordinates for the intended target and for the stars we want to hop from, in order to compute the difference, the kind of movement we have to do in order to hop from our visible target to our intended target. Okay, so let's talk about stellar coordinates and how they are defined. So first of all, what is a set of coordinates? We are all familiar with the classical set of coordinates in the three-dimensional space. So we have here x and y and z. Here we have point P in this space. All these three directions, they are orthogonal to each other. And so if we project P on the xy plane, then we can get the coordinate in the x direction and the y direction of this point. And if we do the same, projecting the point P to the plane yz, we can get the coordinate z for the point P. In this way, we can define the position of every point with respect to the origin of our system of referement. Now, this is not very clever way to define a system of referement for stars. There is a better way, that is the following one. If this we have the horizon and we have a star up there, how we define the coordinate for this star? Well, we can, of course, first of all, we can decide, okay, what is the height of this star over the horizon? Well, it will be difficult to measure it with a measuring tape. So in time, people decide that this was a good idea to measure the altitude of the star, but we need a better instrument. And so they invented the sextant, where we have a swinging arm on a graduation scale that when we point the instrument to the star will tell us the altitude above the horizon. So this angle here, that is called altitude. And also, now that we know how high the star is above the horizon, we need, as for this case, a point of referement to say where is the position of the star above, well, in which direction we can see the stars above the horizon. So we need a standard direction that would be the north, the direction pointing north. And so the angle formed between the direction where we see the stars and the north direction moving eastwards, that angle here is called azimuth. And these are the coordinates that an alt-azimuth follows in order to track the star. And they also depend on the location you are. Imagine a simple example is, look at Polaris. You want to align the mount to Polaris, well, you have to set the altitude of your mount depending on your latitude. So for every star, you have to consider the place where you are, and the location, the latitude of where you are, and also the time. Now, to visualize the time, let's make another nice example. Here we have a nice landscape with some distant mountain. Now, we know that if you frame this landscape and there is Polaris visible somewhere there, and you photograph the landscape long enough, stars will start drawing what is called a star trail. So trails along, well, around the Polaris, and they move in circle. Now, the fact that they move in circle and they form trails means that at a certain point in time, this star was here at a certain position, x, over the horizon, and also with a certain altitude, let's call it y. Now, after a certain time, this star went here to draw this trail. And so we see that now, at the new time, the star is at the point x prime over the horizon and is also lower in the sky. And so you see that this set of coordinates is changing in time, all the time, constantly. So this is not a right set of coordinates I would pick in order to star hop from a visible target to our intended target, because, okay, in the time you are calculating the difference in coordinates, how you have to move the mount, and you have to do everything fast and on the fly and at the location, because the stars are moving. Now, there is a better set of coordinates for this game, and these are called the right ascension and the declination. Now, how are those things are defined? Well, basically, these are spherical coordinates. So we have a sphere, and we have a center of the sphere, and of course we have an equator for the sphere, And this sphere is called the celestial sphere. So basically, all the stars, everything we can see in the sky, is like projected on the inner surface of this sphere. And this right here will be, of course, the celestial equator. Now, how we define this sphere? Well, at the center, this dot here will be Earth. Here we have a North Pole, we have the Southern Pole, and that passing through it, like so, we have the axial rotation of Earth, and then this will be the northern celestial pole, that will be the southern celestial pole, and the equator, the celestial equator, is just the extension of the equator of Earth. Now, we can see that one of the referiments used in order to define this system of coordinates is the rotational axis of Earth. This is varying very slowly in time, and that's why these coordinates, we can assume them to be constant for a big interval of time, like 20 years or so. Now we have one origin here, but we need also to know a standard direction for orientate ourselves along the celestial equator. Now has been chosen as direction, the direction where the star, the sun, our sun, is shining at the vernal equinox. So this will be what is called 0 hour. That is the zero, the origin for the right ascension coordinate. So here we will measure the right ascension moving eastward from the 0 hour, which is where the direction, well, it is basically the direction where we see the sun on the vernal equinox, that is March 31st. So we have one set of coordinates. We move like that eastward and along the celestial equator, and then we are moving in right ascension, and this is defined in hours. So here we have 1 hour, we have 2 hours, we have 3 hours, we have 4 hours, and then we make all the way around. We come back here with 22 hours, we come back here with 23 hours. And so this is one set of coordinates, the right ascension. Now suppose that there is a star that is projected here on the celestial sphere. You want to arrive to these stars. What are the coordinates of these stars in this set of coordinates? So the right ascension will be, I don't know, something like 4 hours. So we have to walk along the celestial equator until 4 hours in right ascension, and then we have to climb above the celestial equator of a certain amount. How much? Well, that will be an angle formed between us, the position of 4 hours, and then the altitude of the star. And this angle here, that is the declination. So we have these two sets of coordinates. So every star has a set of coordinates that are right ascension and declination. And basically, those are constant. They do not depend in time for, well, in a meaningful way for relatively short period, relatively long period of time. And those are global. So every star, every object in the sky has its own set of coordinates. So let's suppose that here we have another star, or our intended target, or our galaxy. Let's say this is a star, and then here we draw a small galaxy that we don't know where it is. We cannot see it, but what we can see is that there is a bright star next to it. So we have here the star 1, and the galaxy is 2 is our intended target, and what we want to do is to jump from one to another. So let's suppose this is, I don't know, let's call the 1 will be Mizar, the star of Mizar, and 2 will be M101. So how do we jump from Mizar to the galaxy? Well, we simply need to compute the difference in right ascension between the right ascension of M101 and the right ascension of Mizar. And then we need to do the same with declination. That will be the difference between the declination for M101 with the declination of Mizar. Great. Because these things, this coordinate, they do not change in time in a meaningful way, you can compute all these differences at home, in the peace of your home, in the comfort of your home, and create your own database for star hopping. Now, when you are in the field, what you simply do is to take your camera, to frame your star, and then apply to the mount difference in right ascension and declination, and where you go is that now you can see in the frame, you see your galaxy. There is how do we move the mount? So when you compute this difference, if let's say if the change in right ascension is negative, then it means that you are moving. That means that your intended target has a lower right ascension than the star you were starting up. And since right ascension increase moving eastwards, then you have to move back you have to move back. So to rotate in counterclockwise direction. So let's suppose this is how we are going for the right ascension. We are moving this way. This will be the north, the south. So if you are behind your mount looking to north, if you have a negative delta, it means that your intended star, your star 1 was here, your intended target is behind, and so you have to rotate counterclockwise. So that will be a counterclockwise rotation. If delta RA is positive, then it means that in our movement, then we have 1 here and we have 2 there, and so we have to move this way. We move in a clockwise direction. So this is how you move. So negative differences in right ascension. If you are looking north, you have to rotate your equatorial mount counterclockwise of the right mount, and if you have positive right ascension, then you have to move clockwise. And also when we consider declination, if you have a delta and declination that is negative, that means that in declination 1 is above 2, and so that means you have to move your camera downwards. And if you have a delta in declination that is positive, then it means that 2 is above 1, and so you have to rotate your camera upwards in declination, to point upwards. And so you see that this is rather simple way to understand how the coordinate works, and also how you can use them in order to star hop. So you just have to do this piece of map. The original coordinate you can get from any software like Stellarium or any application, astronomy application on your phone. So you calculate that, and then you can do that at home. You print your chart, you go on the field, and you see where you want to hop, and so you know already the right correction to implement on the mount. The point is, this method works well on a tracker because anyway we still have a rather wide field of view, and so even if we don't land exactly on the target, the chances are that we will still be visible inside the frame with a test shot, and so we can then fine-tune the position. And this is because the precision we can perform the hopping depend on the precision of the scales, and usually we have a precision of about in a tracker like the Star Adventurer, we have a precision of 5 minutes in right ascension and 2 degrees in declination if we build the proper device to measure changing in declination. And that will be the third part of this video. So I hope it's clear now how we define the set of coordinates. So there are two sets of coordinates. We can work in altitude and azimuth, but those change in time, so they are not useful for star hopping. And instead we work with right ascension and declination, and because of the way they are defined, they do not change fast with the time, so they are constant. They can be considered to be constant over a long period of time. You can compute the difference between the coordinate of a star and your intended target easily at home. Print out the sheet, goes in the field, frame the visible target, apply the proper rotation in right ascension and declination in order to hop to your intended target. And if in doing so the right ascension you calculate the difference in right ascension is negative, you have to rotate counterclockwise. If it's positive, you have to rotate clockwise. And when the declination is negative, the difference in declination, that means that you have to move the camera downwards. If the change in declination is positive, then you have to move your camera upwards. In part 2 of the video, we have understood how we calculate the coordinates in right ascension and in declination, and how we use them in theory to hop from one target to the other. Now, how do we do that in practice? Well, there are many mounts that they offer graduation circles, like the one that are at the back of the Star Adventurer Pro. Some mounts, they have circle both in right ascension and in declination. This is the deck, the declination deck for the Star Adventurer. These circles here, in principle, they are used in order to help you, to allow you to polar align the Star Adventurer in the field without the use of any application or computer or whatever. Just understand how to use these graduation circles, and you are able to polar align your mount in the field. Unfortunately, the manual that comes with the mount is awful in explaining how we set those circles. Most of the people, they say, okay, we don't bother with that. They suggest to beginner not to bother with those circles, just use an application to help you find the polaris and put the polaris in the proper position inside, on the proper position on the reticle that is inside the Star Adventurer. So these circles here, to me, are what set this mount above all the other trackers that are on the market. And we can use these very same circles not only to polar align the mount, but also to calculate changing in right ascension. So this thing is worth the half of Vago 2. Now the problem is that here on the declination deck, we have no graduation circle whatsoever to measure changing in rotation in declination. Now, we know that here we have this fine-tune adjustment knob, and we know that if we do a full turn of it, then we are changing the orientation of the camera in declination of about either 5 or 10 degrees. I don't remember exactly. Anyway, a full turn will probably be too coarse as a measure in order to properly hop from one star to your intended target. So on the market, there are some graduation circles you can use to put on the declination deck of the Star Adventurer, and I will link one kit in the description of this video. And I also will link on the description below a link to a post in my blog where I teach you how to build with parts you can find around in the house or at your home depot a declination circle for measuring changing in declination. So what you need is a protractor or a rigid support so that it doesn't get saggy with condensation in the field. And then you need, if I can rotate the Star Adventurer, if I can move it, maybe you can see it better. Now what you need is also to tape a scale like so on the let's do this will be better. So a scale like this, you just draw it and you tape it on the side of the declination deck, and then you pop the protractor on top facing down, so that when you look at, you have the scale near, well, the protractor near the scale of referiment, and so you can easily measure changing in declination. Okay, so this is how we mount everything. We put our protractor in between the deck and the camera. We have enough of the screw coming out so that we can safely screw and fix our camera. Now we can close the clutch, and this is the interesting part of this protractor. If I can move a bit the camera, you can see probably better. Now the protractor is mounted, the camera is on the top, yet we can still rotate the protractor with respect to this scale here, and this is quite stiff action, so there is some friction, and this friction is what allows the protractor to rotate in sync with the camera when we rotate the fine adjustment knob. And so in this way we can align one mark, like let's suppose the 0 on the protractor to the 0 on the scale, and then if I have to move, I don't know, 5 degrees or 10 degrees, I can simply rotate this one way or the other in order to rotate the camera of the right amount, in this case 10 degrees. Now I will give you a demonstration of how we can use this thing. So in order to give you a demonstration of how the things work, I have set up my room in order to have a star over here, this red spot. That will be the star we will hope from. And then here I have a purple dot, that will be the target we want to hope to. And then of course, in order to have right ascension and declination work in the proper way, I need to align the mount to the celestial pole, which will be this blue dot over here. So the star adventurer is already aligned to that, and now we use a red dot star finder in order to find our visible star, and then we will apply the correction in right ascension and declination in order to hope and arrive to the intended target. Okay, so with the red dot star finder we have framed our star we will hope from. Now this is in the center of the field of view of this 200mm lens, and now what we need to do is to know our position in right ascension and in declination in order to compute then the proper movement to cover the difference between the coordinate of the intended target and the star we are hoping from. So to see where we are in right ascension, what we can do is to look at the graduation circle for the date, and find a mark that line up with a mark in the graduation circle for the time of the day. In this case, June 30, that is this long mark here, lines up with midnight. So this is a convenient way to remember which mark we are looking at during the procedure. So remember the date rather than the long mark that is in between 6 and 7. Just say June 30 was aligned to midnight. Now I know, because I have computed the difference between the two right ascension, that I have to move of a positive value in right ascension of about 4 hours and 15 minutes. So that means that I have to move this mark all the way eastwards, so in a clockwise way of 4 hours and 15 minutes. So what I do in this case is to undo the clutch gently so that I don't lose the polar alignment, or try not to. And then you see June 30 now is moving. We have to pass 2 hours, we have passed 3 hours, we have passed 4 hours, and now we have passed 4 hours 10 minutes and 4 hours 15. Now with this position we can lock the clutch again, so that we did the right movement in right ascension. Now we go to the other side to see what we can do with the declination. For the declination, we don't really care about the position because we can rotate the protractor without changing the orientation of the camera. So we can simply line up whatever we want with the 0 on the reference scale that is taped on the side of the declination deck. In this case, I want the 0 there to line up. I want the 0 there to line up with the 0 of the declination, well, of the reference scale. So now I know that what I have to do in order to hop in declination from the visible star to the intended target is to lower the camera 30 degrees. So I start acting on the declination knob, bringing the camera down, you see it's moving down, until the 30 on the protractors lines up with the 0 on the scale of referiment. Okay, this is quite a big movement. You want to choose a point to start to hop from that is closer to your intended target, so you don't have to do all this kind of manipulation, and that will put less chances that you will throw the camera out of, well, the mount out of alignment. And this is because this is quite a lightweight setup, so whatever movement you do, you see that you are moving everything. Anyway, so this is another story. Now I have moved in declination 30 degrees downwards, and we can go back to the other side and see what we have in the field of view. And sure enough, we have the purple dot there. Now this is not exactly in the same position where the red dot was. So in principle, if everything was as accurate as possible, then you would have the star where you hop from and the target where you arrive to in the same position on the frame if you center them. But okay, this error is good enough in order to have it's good enough for us in order to see at least the target in the field of view of our instrument, and then we can simply refine the position, take a couple of test shots, and we are good to go. So if this is a very small galaxy that we cannot see it, and we have a bright star that is nearby, once you get the grasp on the method, it takes like 2 minutes to move from the visible star to the invisible galaxy. Okay, in this video we saw how we can use star hopping in order to frame an invisible target for astrophotography, say a small galaxy, starting from a bright star that is nearby and it is easier to frame with a red dot star finder. We saw how we can configure the Star Adventure to do star hopping. We know that half of what we need is already there and are the graduation circles at the back of the unit. And also we know that we can buy or we can make a custom-made protractor in order to measure changing in declination. And this will allow us in no time to do this star hopping, and to frame any kind of target with any kind of instrument that we can throw on this kind of mounts. And I hope this was useful, and let me know in the comments if it works well for you.